going to take a look at something called conducting the thermal gradient. So what you see in front of you here is a wall system. And so it's a little schematic that shows masonry. It shows a layer of plywood, so for sheathing, and it shows a layer of batt insulation, fiberglass batt insulation. And finally, on the interior side, there is a layer of gypsum board. The dimensions are shown down here below. So this is in millimeters. These are, obviously simplified in the numbers here, 100 millimeters for masonry and 15 millimeters for the plywood and so forth. So in reality, these numbers are going to vary depending on what sort of materials you're actually using. And you'll see that some of those will conform to dimensional lumber sizes. So you're going to find things in feet and whatever, but this is just in metric, in millimeters here. And we're just doing this for a instruction purpose. So all of those material conductivities we can look up. So I provided them in a brief list here. So masonry, plywood, fiberglass batt, and gypsum. And so these are approximate values for the thermal conductivity. We'll note the temperature outside is 0 degrees. So we're looking at this application in the winter time. And as it will typically stand, the interior temperature we can often treat as being 20 degrees Celsius. So seldom will that change, and if it does, it's only by a few degrees. So what we're going to look at today is we're going to look at the thermal gradient. And so there's going to be two parts to this. The first part is we're going to have to analyze this system in terms of its thermal resistance for each and every layer. And we're going to have to figure out what the total RSI of the system is. And then we're actually going to come back and take a look in the second part of this, and we're going to figure out the thermal gradient. And essentially that is the temperature which we can expect all these different components to be at in a given steady state condition. So for instance, if it's 0 degrees outside and it stays 0 for an extended period of time, we'll be able to figure out what the temperature of each layer is and even everything in between. So this will be helpful because we'll come up with this thermal gradient, which we'll end up drawing over top of this schematic here. And then we're going to use that in another application that comes later on, where we take a look at the influence of moisture and particularly vapor and condensation. So this is part one, and we'll get into part two, and then later we'll actually have an application for this. So let's go on to the next slide. Okay, so what you see here is the wall system, and I've got a table here. So you can make a table similar to this or copy this directly. But what you want is you want to have sort of a list of all your layers, and you want to be able to essentially determine the thermal resistance of each layer and then find the total thermal resistance. Now, we see that there's 4 different layers here within our wall schematic, but we also want to consider the air films, right? So there's going to be an exterior air film. So that's the exterior AF, and also the AF on the interior. So the interior and exterior air film, these are these little micro layers. They're not actually material, but it's just a blanket of still air that exists over top of that surface, and they add a little bit to the thermal resistance. So I'll walk you through how we do this. And what we can do is we can enter in each material in this list here. And it doesn't matter if you work from exterior to interior to exterior or exterior to interior. You just want to keep this in chronological order. So I'll start with the exterior in this case. I'll put exterior air film. And I can write down the remaining materials as well. So I'll put those in. I'll put masonry. So that's the next one that goes over. And then it's plywood, fiberglass batt, gypsum and the interior airflow. Okay, now I'll just give a little note here. We don't have a conductivity or a thickness for these layers, but we know the conductance, and that's because we know it by looking it up in those ASHRAE tables. So I'm going to just write that in here. For the exterior, I believe it was 34, I think, and then that became 0.03. And I'll go ahead and I will do the interior air film as well. So I think this was 8.3. Okay, now to fill out the rest of this table, we just go to each layer. So for instance, for masonry, and we enter in the conductivity. So conductivity for masonry, here we've got 0.8. The thickness of that layer, if I look down here, I have 100 millimeters. So that's going to be 0.1 meters. So always put in meter units. And if we find the conductance of that, so thermal conductivity divided by the thickness, so that's going to be 0.8 divided by 0.1, so that's going to give us 8. And then the thermal resistance, so that's going to be the inverse of that. If I go 8 inverse, so that's going to be 1.25. Is that right? So not 1.25, 0.125. Okay, so you just fill that out and calculate that for each row. And you're going to come to the thermal resistance for each layer. So I'll do one more, and then I'll just fast forward through this. Plywood. Okay, and now I'm going to just add all of those up. So if I get my calculator here to give me a hand. Okay, so I get 2.448. I'll just put 2.45. Should be close enough. And so that is the thermal resistance for this entire wall assembly. So we've done part one. Okay, so now what I'm going to do is I'm going to look at part two. And this starts off by first looking at identifying the proportion that each layer of this system is responsible for, or should I say, its portion of the RSI. So for instance, the insulation is going to be the layer which has the largest portion of that thermal resistance. So remember that our thermal resistance was, total thermal resistance was 2.45. Okay, so of this 2.45, if we look, we actually see that fiberglass bat, it was responsible for 2.0 of that RSI. So the majority of that thermal resistance comes from the fiberglass layer. Okay, so if I look at each layer and I take the RSI of each layer and I divide it by the thermal resistance of the entire wall system, then I actually end up with the proportions in terms of percent. And we'll get to why that's important. So I'll just put down what this is. So if we take 0.03 and we divide it by 2.45, we're going to get something close to 1%. And if we do this for 0.125 and I calculate that, so I go 0.125 and I divide it by 2.45, we get 0.51. So we'll call that 5%. I'll just fill these in for the rest of them. So the plywood is about 4%. The fiberglass ends up being close to 81%. It doesn't have to be exact, but you want to get fairly close. And then 4%. And lastly, the interior air film actually has 5%. Okay. Now, this shows us the proportion. From this, we can actually start to begin to determine the thermal temperatures throughout this wall system. Well, how do we do that? First, we got to remember what the temperature differential is, right? So temperature on the inside was equal to 20 degrees. The temperature on the outside was equal to 0 degrees Celsius. So therefore, the temperature differential is going to be 20 degrees Celsius. So that's the difference between the interior and the exterior temperature. Okay, so if we multiply the percent by the temperature, so that would be 1% multiplied by 20 degrees Celsius, we're actually going to determine the increment of change through each layer. So let's just try with an example of 1%. So we go 1% of 20, so I have 0.5 degrees Celsius. Or go 5% of 20, I get 2 degrees Celsius. And then 4%, it's 1.6, 81. So it's like I've overestimated it here. So that's okay, start again. This makes sense. 0.2, 1, 0.8, 16.2, 0.8, and 1.0. Okay, so each layer is going to result in a temperature change of this amount. Now, if we consider that the surface temperature on the exterior is going to be 20 degrees Celsius, or sorry, 0 degrees Celsius. So 0 degrees Celsius on the exterior, TO. That means that when it passes the air film, it's going to go from 0, and we're going to add this 0.2. We're going to put it down here. So we're going to get 0.2 degrees Celsius. Okay, so that means when you're just outside the wall surface, you're at 0 degrees. But as soon as you get right up to the surface of that wall, the temperature actually increases to 0.2. So not much, but there's a slight increase. And that's the temperature change that occurs along the air film. Okay, so it's a very small amount on the exterior, but we will include it, and we'll go on to the next one. So masonry. So as we go through the masonry, there's going to be a 1 degree temperature change. That means at the start of the masonry, we start at 0.2 degrees Celsius, but by the time you get to the back of the masonry, so this area of the masonry, we're going to have a temperature of 1.2 degrees Celsius. The plywood, well, that's provides a temperature change of 0.8. So this brings 1.2, like this, and add that in, it becomes 2.0 degrees Celsius. So it's still quite cold all the way up to the inner surface of the plywood. Now, if I go to the fiberglass batt layer, we see that there's 16.2 degrees Celsius in temperature change. So we're going to add 16.2 to the 2, and that's going to be 18.2 degrees Celsius. And if I add 0.8 to 18.2, then I should get 19 degrees Celsius. And that's brings us to the end of the interior side of the gypsum board. And then with that air film is going to provide 1 degree temperature difference. And that brings us to 20 degrees Celsius. So one way of checking this is when you get to the end, you started at 0. And if you added all these numbers up together, it should bring you to 20, which indeed it does, which was the interior temperature. So it seems like mathematically everything here works out. And what this represents is the temperature of the inner and outer side of each layer. So for instance, the inner side of the masonry is at 1.2 and the exterior side is at 0.2. And we can mark all of these onto a plot, and then we can determine what the temperature gradient through this wall system is. So what I'm going to do is I'm going to pause this here, and then I'm going to come to a new slide here, and we're actually going to draw the thermal gradient onto this wall system. Okay, so what I've done is I've laid out a grid over the wall schematic here. And if I label this grid, I'm going to put start with 0 degrees Celsius, with 5 degrees Celsius, 10 degrees Celsius, 15, 20, and 25. So now I've shown this temperature grid that goes through the wall system. Now, the cool thing which we can do is I can actually come to any part of the layer of any certain material on the inner and outer side of it, and I can actually enter in these surface temperatures. So for instance, on the air film, so that's the area just outside of off the face of the brick, and we can exaggerate this a little bit. So I'm going to put it as being right here. I'll put a little marker there at 0. Okay, so that one's done here. Okay, go to the between the air film and the masonry. So that's right on the surface of the masonry. And that is going to be 0.2 degrees Celsius. So it's really not too high up there. It's going to be somewhere around there. And so that's the temperature on the surface of the masonry. So I've done that one here. Now next, I'm going to take a look on the interior side of that masonry. So we're going to use 1.2. I use 1.2, so I just got to approximate here. So perhaps it's around here. Again, we don't have to be exactly exact. And you'll get more detail if you draw a better grid than what I've drawn here. And so we get to the plywood surface. On the other side of the plywood, it goes up to 2 degrees Celsius. So I might be a little bit off on my drawings here, but that's okay. You can do a better job. Now, as it goes through the bad insulation layer, so it starts off between the plywood and the fiberglass, it's 2 degrees Celsius. But as it goes through that and it gets to the inside of the gypsum board, we see it goes all the way up to 18.2 degrees Celsius. So 18.2 is going to be somewhere around here. I've drawn that there. And so now the temperature's all the way up here as we get to the interior side of the gypsum board. It goes up further. So I got that one done to 19 degrees Celsius. And then, of course, after it passes through the air film, we get up to 20 degrees Celsius. So pretty simple stuff. And if we connect these dots, draw a line. We draw a line through all of these. We actually get the temperature profile. So this temperature profile is what we would expect if the conditions were to be 0 degrees Celsius on the exterior, and on the temperature interior is 20 degrees Celsius. So we would get a temperature profile like what you see here under steady state conditions. Now, there's two things we can use this to look at. Is obviously we can analyze different wall systems and the effect of thermal bridging. So what happens where you don't have this insulation in the middle, like for instance, where a wood stud takes up that cavity space, what is our thermal profile? So we can use it to identify things like thermal bridging. But the other building science application that we're going to look at is what does this mean for things like condensation and the properties of water vapor when introduced into the wall cavity. So we'll take a look at these sort of applications, but this is the process which you can follow to do your thermal gradients. Now, if you have different layers or more layers or less layers, you can do it in the same process. You just have to make sure you use the appropriate amount of layers. And in best practice, always use the exterior and interior air films. In some cases, it'll make a little bit of a difference. In this case, air films were about 6% of the total RSI. So not much, but they can have some impact.